Welcome back to the channel. Previously, we developed this one-dimensional linear wave code in Python, and we're using Leapfrog integration to step through time. We can see that our Gaussian wave pulse hits the edges, which have fixed boundary conditions, and in 2 wave travel times, we see the peak reconstructed our initial condition. Now, why is it 1.98 and not 2? This is because the wave doesn't actually travel to the ghost cells, the boundary cells. So because I have a grid spacing of 0.01 here, I'm going to be 2 times that less will be my actual travel time for the wave to travel to the edge and back twice. So another thing we'd like to check to see if this wave is behaving as expected is that we would like to plot the initial condition in addition to the current condition. So to do that, I'm going to import this module copy. And then after I've defined my initial condition here you can see the definition of the wave pulse. Let's say that orig, for original, equals copy.deepCopy of f of colon comma 0. Remember, that's the 0th time slice in our past, present, future paradigm. So what this is doing is making a copy with a different memory location, so it's completely independent from our f of colon comma 0 there. It has the same value. We're not going to advance that value, but we're going to plot it on these axes. We'll plt.plot x comma orig, and for this one, let's do just a simple black line, and let's get rid of our ball and stick appearance here. So rather than b-0, I'll just have b for blue. Now, if we plot this again, we can see the initial condition staying there, the reflected pulse, and we're hoping that these lie directly on top of each other when we take a look. And let's zoom in. We can use our magnifying glass tool here. So I cannot even see a difference between the two curves. But we haven't run the code for that long. So let's run it for a little bit longer. I have a structure here. If k mod 1 equals 0, then do the plotting. So I've indented this block, I have my if clause here. If I only want to plot every 10th frame, I can make this a k mod 10. The mod operator just takes the remainder when I divide k by 10. So if that's 0, it means we have a multiple of 10. Let's take a look if we run for much longer, let's say 10 times longer, and only plot every 10th point. The longer we do this integration, which is numerical, it's not perfect, the more error we're going to accrue. And it looks like we didn't quite hit the time step we wanted. Because of our mod operator. So let's run all of those time steps. I will fast forward a little bit here. So here we are at 20 wave travel times, and let's take a look at the match between our initial condition and our blue plot here. We can see that we still have pretty good matching there. Let's see if we look at the actual data. What is, we have, the quantity we're plotting is f of colon comma 2, and let's subtract orig from that and see what the difference is. So we do have these very small numbers, 10 to the minus 44. They get as big as 10 to the minus 16. These quantities. Why don't we actually plot those? So I'll hit my up arrow here and plt dot plot. I'll close my other plot here. But plt dot plot x comma f of colon comma 2 minus original. And let's make that blue and see what that looks like. So we have this very small noise that has accrued in our data. It still looks acceptable as a physical simulation of the system. Let's reduce our time back down, so we'll run a shorter simulation. Previously, I alluded to the CFL condition, which says we can't allow the wave to move more than one grid spacing per discrete time in the code. So the time step is 1 times dx over the wave speed. Let's see what happens if we make that very slightly bigger, so the wave is just overshooting a grid point and we're losing information. I've made 0.1% bigger than it's allowed to be, and let's watch the simulation. So far, everything looks good. And nothing catastrophic happened there. Let's make this 1% bigger than what is allowed and see if it is still stable. So here we have that noise that came into the data because of overstepping our time allotment, according to the CFL condition, and things go out of control, the energy in the code just blows up. So we've tested a few initial conditions, and we've checked the stability of our code. We could even make this a little bit lower to have it be beyond stable. Let's check one more initial condition. I'd like to make a triangular wave pulse. So the way to do that, I always say don't retype code if you can copy it. So let's copy what we're setting this equal to here. I would like to have from 0 up to int of, let's say, npts, remember that's our number of grid points, the length of x, divided by 4. So if this turns out not to be divisible by 4, we will just take the integer part. And let that equal to 4 times x of those same grid points. So copying there. And remember that the colon means, if nothing precedes it, it means start at 0. So our first quarter of the simulation space is a line of slope 4. Now, to come back down, we're going to let our ending point from that definition be the starting point for our next one. So we'll go from int of endpoints over 4 colon will take me from that point to the end, and moving the colon here. And we want this to be a slope of -4/3, and then we will add 4/3. So this should give us a triangular wave pulse. Let's take a look. There we can see our initial condition. This is peeling down as expected. There's a reflection point, and based on everything we've seen so far, this should reconstruct the initial condition, and it does. Very good. So now that we feel in control of physical reasonableness of this simulation, at least for the amount of time that we're integrating, the next step to make this a little bit more realistic is to bring it to 2 dimensions. So up next, we will see how to take this code and 2-dimensionalize it. We will turn all of our 1-dimensional arrays into 2-dimensional arrays, and our 2-dimensional arrays into 3-dimensional arrays, and it will be pretty straightforward. I will see you in the next episode.